In this section, you'll learn how to calculate eigenvalues and eigenvectors. The formal definition for eigenvalue and eigenvector is here, and the key is that AX equals lambda x. This lambda is your eigenvalue, and the x that's in both those spots is your eigenvector. And notice that AX equals lambda x will always be true if x is 0, so they're only eigenvectors if it's a non-zero vector. In exercise 1, we are given matrix A and want to show that the vector 1, negative 1 is an eigenvector of A, but 1, 1 is not. So what I want to do is look at what AX is. So multiplying these two. So I have 7 minus 2 is 5, and then negative 4 minus 1 is negative 5. Notice that is 5 times 1, negative 1. So I have AX equals lambda x. So here my eigenvalue is 5, and my eigenvector is 1, negative 1. I'm going to do the same thing for AY. When I multiply A times Y, I get 9, negative 3, and that is not equal to some number times 1, 1. So that means that 1, 1 is not an eigenvector for that matrix A. Exercise 2 asks us to show that this equation, AX equals lambda x, is equivalent to A minus lambda IX equals 0. So I'm going to start with my AX equals lambda x, and I'm going to subtract the lambda x from both sides. So I get AX minus lambda x equals 0. And then I can factor out the x. But because the x is on the right side, it has to stay on the right side. And I'll have A minus lambda. But I can't, A is a matrix and lambda is a scalar, so that subtraction does not make sense. So to make it make sense, I do lambda I, and I get that equation, A minus lambda I x equals 0. We will be using this a lot to find eigenvalues and eigenvectors. Exercise 3 asks, is lambda equals 3 an eigenvalue for that matrix? To find out if lambda equals 3 is an eigenvalue, we need to know that A minus 3I x equals 0 has a non-trivial solution. Say if it does, then it is an eigenvalue. So let's start by doing A minus 3I, and that's going to be so look at the homogeneous system. A minus 3I times x equals 0. If you row reduce this, you'll see that we have a free variable, which means there is a non-trivial solution. So lambda equals 3 is an eigenvalue. To find a corresponding eigenvector, I need to solve this homogeneous system. So x3 is free, x2 is 2x3, and x1 is 3x3. So I could say 3, 2, 0 is an eigenvector that corresponds to the eigenvalue of lambda equals 3. The eigenspace of a matrix is just the span of the eigenvectors. So space implying that it is a vector space or a subspace. In exercise 4, we want to find a basis for the eigenspace corresponding to each eigenvalue. So let's do lambda equals negative 4 first. We want to look at A minus lambda I x equals 0. So a minus negative 4 would be plus 4i x equals 0. So that's the system. I'm going to add 4 to my diagonal entries. So I'm going to get 5, 6, 5, 6. Augment with zeros and solve this. So I have 5, 6, 0, 0, 0, 0. I see that x2 is free, and this first row is 5x1 plus 6x2 equals 0. So x1 is negative 6 over 5x2. So negative 6 over 5x2. So the basis for my eigenspace corresponding to negative 4 would just be negative 6 over 5, 1. Or you could do, let's say x2 equals 5, then my x1 would equal negative 6. So there's lots of different possibilities for a basis, any linear combination of that one vector. For lambda equals 7, I'm going to look at a minus 7i x equals 0. A minus 7, I'm going to subtract 7 off the diagonals. 1 minus 7 is negative 6, 6, 5. 2 minus 7 is negative 5. Augment with zeros. I'm going to get negative 1, 1, 0, 0, 0, 0. So I have that x2 is free, and my x1 is, let me change that to that multiply by negative 1. I will get positive x2. So a basis would be like 1, 1. So basis for eigenspace corresponding to lambda equals 7 is 1, 1. So in general, if you're trying to find the basis for the eigenspace, you just want to solve the homogeneous system a minus lambda I x equals 0. I want to point out that you are finding a basis, not the basis, so there are many different possible answers. Let's try this with a 3 by 3. Let's find the basis for the eigenspace corresponding to lambda equals 2, and I'm going to describe the eigenspace geometrically. So I'm going to look at a minus 2i x equals 0. I'm going to subtract 2 off my diagonals. So I'll have 2, negative 1, 6, 2, negative 1, 6, 2, negative 1, 6. Oops, forgot to augment with zeros. Notice all the rows are multiples, so I'll have 2, negative 1, 6, 0, 0, 0, 0, 0, 0, 0, 0, 0. So x2 and x3 are free. And then the first row tells me 2x1 minus x2 plus 6x3 equals 0. So if I solve that for x1, I get 1/2 x2 minus 3x3. Rewriting it, separating my x2 and x3, I have 1/2, 1, 0, and negative 3, 0, 1. So that can be a basis. So I have 1/2, 1, 0, and negative 3, 0, 1. So that is the basis for my eigenspace corresponding to lambda equals 2. Notice it has 2 vectors in R3, so the geometric description would be it's a plane in R3. So just some special cases, we have that the eigenvalues of a triangular matrix are the entries on the main diagonal. So if you have a triangular matrix
or a diagonal matrix, the eigenvalues are just the main diagonal entries. And if the matrix is not invertible, then 0 is going to be an eigenvalue. So exercise 6 just says, by inspection, find an eigenvalue and a corresponding eigenvector. I notice that these two are multiples of each other, so the columns of this matrix are linearly dependent. Which means A is not invertible, which means 0 is an eigenvalue. So that tells me A minus 0 I, x equals 0. To find a corresponding eigenvector, I can solve this. So really that's just ax equals 0. When we row reduce, we get this. We see that x3, actually x2 is free, x3 is 0, and that x1 is negative x2. So if I'm just trying to find a corresponding eigenvector, I can let x2 be anything. So if I let it be 3, I have negative 3, 3, 0 is an eigenvector corresponding to lambda equals 0.